Good morning, sir.
Yeah, good morning. Is my screen visible?
Yes, sir.
Okay. So, are there any questions, doubts? Yeah, if anybody has any question, doubt, you can ask.
Hello, sir.
Yeah,
So actually, in classical plate theory and in the
yeah.
first order shear deformation theory, why didn't we take the triangular element in case of the classical plate theory? But
No,
here we are taking
triangular element we took in case of first order shear deformation theory.
yeah, sir. So that's the question. Like, why didn't we take in the plate like classical plate theory?
We can do in classical plate also, but the in that also the compatibility condition will not be satisfied. Although we can take. So say we can have a three-noded triangular element with say 3 degrees of freedom w del w by del x del w by del y at the
Yes.
corner node, and then we can formulate that element also, but it will be in incompatible element.
No. Thank you, sir.
Yeah. So are there any other questions? Okay, so then let me start. So last class I was just discussing methods to eliminate shear locking. So screen I'm not able to write, so let me close and then open it again. Is the screen visible? Hello, is my screen visible?
Yes, sir. Yes, sir. It is visible, sir.
Okay. So last class I was just discussing methods to eliminate shear locking. So I had told you three methods. So let me discuss one by one each of these. So the first one we discussed was reduced or selective integration technique. Selective integration technique. So yeah, in this, what is done is that basically locking is introducing extra stiffness. So to reduce that stiffness, we do the reduced integration. So what is happening exactly in locking? That is due to locking transverse shear stiffness, mainly the transverse shear stiffness, transverse shear stiffness matrix is overestimated. Overestimated means it is when we do the full integration for thin problems. So this stiffness is why it should be negligible. So, but it is overestimated. So transverse shear stiffness matrix is overestimated, and to eliminate this, over stiffening, reduced or selective integration is used. Reduced or selective integration is used. So let me now, how do we do this? So that let me discuss. So first let us take an example of four noded isoparametric quadrilateral element. Formulation of this element we have already discussed. Isoparametric quadrilateral element. So as you know, in this element what we are doing is, in the physical coordinate space we have a arbitrary quadrilateral. Nodes are 1, 2, 3 and 4, and this is mapped to natural coordinate space wherein the element is a cube, is a square. So now in this case we know the problem is with the stiffness matrix. So we have seen that the stiffness matrix for this case is written as, when we use the Gauss quadrature numerical integration, so I equal to 1 to m, j equal to 1 to m, and then we have B transpose into D into B into determinant of J, and this whole thing is evaluated at xi I eta j into wi wj. So this is the bending part of the bending stiffness term coming from curvature. And plus we have other term which comes from the transverse shear stiffness. So I equal to 1 to ms, j equal to 1 to ms, and then we have bs transpose into e into bs into determinant of j evaluated at xi I eta j into wi wj, and this is transverse shear stiffness term. So now what we do, there are two things, reduced integration and selective integration. So what is done in reduced integration? So when we talk of reduced integration, so in this both the stiffness terms are under integrated. Both means bending as well as the transverse shear. So both the stiffness terms are under integrated. That means we use the, so what under integration means is a lesser number of Gauss points are used than needed for the exact integration. So this is known as the reduced integration. That means both stiffness terms, that is bending and transverse shear, both are under integrated. So we use the lesser number of Gauss points to evaluate the integrals, and that is known as the reduced integration. Then in the selective integration, what is done is only transverse here is selective means some selected term. So as the name suggests, selective, so there is a selected term, and here that term is transverse here because that is the one which is causing the shear locking. That is the main term. So in this transverse shear only transverse shear stiffness term is under. stiffness term is under integrated. So now this we are continuing with this four noded element. So in this
Sir,
when we do yeah,
sir, how this stiffness matrix is overestimated due to this shear locking?
yeah, that I explained, that the theta x becomes very small. So del w by del x plus theta x and del w by del y plus theta y. That term, the contribution becomes larger compared to the bending term. In case of thin saturation, if the same this shear deformable element is used in thin saturation, so compared to what this transverse shear stiffness would be, because no theta x and theta y are tending to zero, so this stiffness goes on the higher side.
Okay. Okay, okay.
So then now see, if we talk of full integration, so we have already discussed that if we are having a four noded isoparametric element, so in full integration the bending term we are evaluating using 2 by 2 integration, that is 2 points along xi direction and 2 points along eta direction. So that is known as 2 by 2 2 by 2 integration. Whereas the transverse shear term, is also integrated using 2 by 2 integration rule, 2 by 2 Gauss quadrature numerical integration. Now in the reduced integration, what we do, bending, because reduce means both the terms are evaluated using lesser number of Gauss points. So bending term is evaluated using one by one. That is basically only 1 point in that case. 1 point in xi direction, one in eta direction. So that would be only 1 point. And the transverse here is also, he also evaluated using one by one integration rule. But the problem is, in this, the stiffness matrix becomes under evaluated. So the stiffness matrix, is significantly lower compared to what it should be. So it over predicts the deflection in that case. So then what we do is we use what is known as selective integration. So in the selective integration, bending is evaluated exactly. So that means bending is evaluated using 2 by 2 integration rule, but the transverse shear is evaluated using 1 by 1 integration rule. So to depict this, what I am saying is, if you look at the element in the, so we have xi and eta. So reduced integration means for both bending as well as the transverse shear, there is only one integration point. So reduced integration. And in the whereas no the in this is I'm talking in the selective integration, what is done is, if you look at the bending, so bending is evaluated using four integration points, that is 2 by 2 integration rule. So this is for the bending, and the transverse shear is evaluated using one integration point. So there is only one integration point. This is the transverse shear. So this is selective integration. So we prefer to use selective integration basically. So in the selective integration, bending term is exactly evaluated. Number of Gauss points, whatever number of Gauss points are needed for the highest degree power of xi and eta. So we decide the Gauss points based on that. But transverse shear is under integrated. That is, we use a 1 point integration rule. So that is just 1 point. Xi equal to 0, eta equal to 0, and w1 will be 2. W1. So that's the only term, W1 into W1 would be 4. Now, why this selective integration eliminates the locking? Because we have seen that when we exactly integrate, so then we are kind of modeling the transverse shear distribution over the entire element. So then we have seen those constraints which are making theta x and theta y either linear function of y or linear function of x, and depending on the boundary condition, the plate is becoming stiff. So now if we evaluate the transverse shear strength only at center point, that is I equal to 0, eta equal to 0. So that would be a constant term, and constant term has got contributions from W as well as theta x or theta y. So that does not lead to spurious constraints. So that is how it eliminates the locking. So the let me write that selective integration eliminates eliminates this transverse shear locking, because gamma xz and gamma yz are evaluated at, to evaluate the stiffness matrix, ultimately you are evaluating the transverse shear strength only at center at xi equal to 0, eta equal to 0. And this leads to the only the gamma xz and gamma yz are evaluated at center of the element, and therefore only the constant term is modeled effectively. When you look at this expression for gamma xz and gamma yz, the constant term is only modeled, is effectively in the incorporated in the stiffness matrix, and that has contributions from both W and theta x or theta y. So without no individually making theta x terms to 0, that constraint is satisfied. So this leads to consistent constraints and no locking. Consistent Consistent constraint means constraints which have contribution from both W and theta x or theta y. So it leads to consistent constraints, and consistent constraints do not lead to any locking. So then there is a no locking in this case. So this is for the four nodal elements. So what you need to do is use 2 by 2 integration for evaluating the bending stiffness matrix, and only 1 point integration for the transverse shear stiffness term. And this will eliminate the locking problem if you are using this shear deformable plate element for thin plate problems. And of course, if you are using for thick plate problems, then you need not do a actually this selective or reduced integration. If you do that, there would be problems. So that also I will discuss. So now let me then also discuss how do we
Hello,
do
sir.
this. Yeah,
Sir, even when we do selective integration,
yeah,
instead of 4 points, we use only 1 point.
yeah.
Uh, then why do we call it integration?
Why?
Why do we call it integration? Means, is it equivalent to integration
Yeah,
if
it
we
is
use it?
equivalent to, yeah, still we are integrating that stiffness. No? So whatever we do over here, see, we are by evaluating the stiffness matrix by converting the integration into summation. So we are doing this summation, which is equivalent to integration. Now, in selective integration, what we are doing is we are evaluating this term for the four nodal element using 2 by 2 integration, 2 points in xi direction, 2 points in eta direction. Whereas this transverse shear stiffness term is evaluated using only one integration along xi and eta. So that means effectively only one integration point. So because this integration is evaluated as a summation, but still we are kind of doing the integration. So that is why this is referred to as integration. Although we are doing summation, but this summation is equivalent to the integration. So we essentially we are doing numerical integration. So numerical integration, instead of explicit integration, you are having this summation.
Okay, so
Okay.
basically, instead of integrating exactly, we are integrating it in an approximate manner.
Yeah, yeah. Now we see, if we use 2 by 2 integration, and if element is a rectangle in the physical coordinate space, then 2 by 2 integration will exactly evaluate that integral. So by using just one by integration point, we are under integrating that. We are not taking the total contribution.
Okay, sir.
Yeah. So now let us how do we do this in the 8 noded element? So 8 noded element. So we have already discussed now the formulation of this element. So I will just in the physical coordinate space see this element can be have the, it can be quadrilateral, it can have curved boundaries. Corner nodes are numbered as 1, 2, 3, 4, and then mid side nodes are numbered as 5, 6, 7, and 8. And then this is mapped to a square in the natural coordinate space, chi and eta. So corner nodes 1, 2, 3, 4, and mid side nodes are 5, 6, 7, and 8. So in this we have already discussed that in full integration bending is evaluated using bending stiffness term is evaluated using through 3/3 integration, and also the transverse shear stiffness term is also evaluated using 3/3 integration. So that is what we do in the full integration. Then in the reduced integration, which is not preferred, so in the reduced integration bending is now one order lower. So bending is evaluated using 2/2 integration, and the transverse shear stiffness term is also evaluated using 2/2. Sometimes instead of 2/2 we may also want to use 1/1 because 2/2 also may lead to some little bit of locking. So and then in the selective integration, in case of selective integration, what we do is bending is evaluated exactly. So bending is done using 3/3 integration, whereas the transverse shear is evaluated using 2/2 integration. And as I already said that the selective integration is preferred over reduced integration. Selective integration, because the problem is coming from the transverse shear stiffness terms. So if we under integrate that term, the element performs better. So selective integration scheme is preferred over reduced integration. Now, as I said, I mentioned that there are problems, associated with reduced or selective integration when this element is used for thick problems, thick plates. If you use it for this selective integration for thin plate problems, then there is no issue. But if you use the same element, that is with reduced integration, selective integration, if you use it for solving thick plate problems, then it leads to the under prediction of stiffness and over prediction of the deflection. So that problem also has to be handled. So as I said, there are problems associated with problems associated with reduced slash selective integration. Yeah, in a class cell. I have a class right now. So now in this, let me explain right first. So as I said, that for thick problem it creates problem. So if under integrated element, if under integrated element is used for thin structures, that is we are talking about plates here. Na by H is greater than 30, let us say for isotropic plates. It predicts that is the element. It predicts accurate results. But if it is used for thick plates, that is the under integrated element. But if it is that is the under if the under integrated element is used for thick plates, say A by H between 5 and 20, problems would be more towards 5 and 10. So, but if it is used for thick plates, the deflection is, that is W, deflection W, the deflection is over predicted. You can say that, in other words, that stiffness is under predicted. So now what actually happens, what we call here is that element leads to extra when you just analyze only a single element. So that means we take the stiffness matrix of the single element, find out its eigenvalues. So of course, know that should represent a rigid body mode. So rigid body modes means zero strain energy and zero frequency eigenvalues. But see, if it is a plate element with W, theta x and theta y degrees of freedom, then it should have exactly 3 rigid body modes. But if you are using for thick plates under integrated element, so then you will find that there are more than 3 zero eigenvalue modes, zero energy modes, and those are known as the spurious modes and also referred to as hourglass modes. So when this element is used for thick problems, element leads to extra zero energy modes. Energy means basically strain energy. So zero energy modes. These modes are also called as spurious modes. So which are not the correct, physically correct zero energy modes. So that is why they are also called as spurious modes, or there is another term called hourglass. These modes are kind of the pattern is similar to when we hit a glass and then observe the crack pattern. So it is similar to that. So that is known as these modes are known as hourglass. So since this problem is there, so what is recommended is that if you are solving thick problems, so for thick plates, use full integration for both. Use full integration, and for thin plates, use selective integration. Use selective integration. Now what is done is if you develop an element or you want to test an element even in the packages, so you do an eigenvalue analysis of a single element. So that means you just take a plate depending on what you want to analyze, thick or thin, and then carry out its eigenvalue analysis, and then check how many zero eigenvalues are there, what are the corresponding modes, whether they are physically correct rigid body modes or whether they are the spurious modes. And if spurious modes are present, then that element would over predict deflection. So to investigate the zero energy modes, eigenvalues of stiffness matrix are obtained. Eigenvalues of stiffness matrix are obtained. So that is what you do is you take just one element. So you have element level stiffness matrix, and although no the individual element stiffness matrix is singular, but you can you cannot invert it, but you can always find out its eigenvalues. That is possible. So you have KE is equal to eigenvalue problem is lambda into DE. So here no in this this is lambda is eigenvalue and this D is eigenvector. So now if you look at this element stiffness matrix KE, so the size of this is 12 by 12 as you know for 4 noded element, 4 noded element. So total eigenvalues you will get is actually 12 eigenvalues. So for this, out of those 12 eigenvalues, 3 would be correct rigid body modes. 3 eigenvalues, 3 eigenvalues, eigenvectors will be physically correct rigid body modes, or these will have zero strain energy, so they are zero energy modes. And similarly no on the remaining, if the element is not having any problem, then the remaining 9 eigenvalues should be non-zero. And no if it is correct, but if we have more than 3 zero eigenvalues, so those extra zero eigenvalues and corresponding eigenvectors would be spurious modes. That means the strain energy corresponding to those modes would be zero, but they are not physically correct rigid body modes, so they lead to over prediction of deflection. Those modes, when those modes are activated, they over predict the deflection for under integrated elements. And similarly we know that this stiffness matrix of size 24 by 24 for 8 noded element, and the degrees of freedom are same w, theta x and theta y. So this should also have no 3 eigenvalues, eigenvectors will be physically correct rigid body modes. The remaining eigenvalues should be non-zero, and there would be corresponding eigenvectors. But if we are getting the more than 3 zero eigenvalues, so then the extra zero eigenvalues would be corresponding to spurious or hourglass modes.
Sir,
So
why
yeah,
only three eigenvalues should be zero?
yeah. 3 means because no the element has got. So if you look at the element has got 3 degrees of freedom, w, theta x and theta y. So it can represent only, say if this is x, y and this is z. So it can have a because w degree of freedom is there, so it can have a rigid body motion along the z direction. So that is no w in this direction, that can be one rigid body mode, that is without deformation the play element just moves along the z direction. So if there is no deformation, the strain energy is going to be zero, eigenvalue will be actually zero. And similarly it can have rotation about say x axis. The plate rotates about x axis as a whole, so without any deformation, so that will also have zero eigenvalue. And similarly the plate can rotate about rigidly about y axis, so that will also have no the rigid body motion, no deformation of the plate, only rigid body rotation, so the eigenvalue would be zero. So because we have only 3 degrees of freedom, w, theta x and theta y, so this plate element can have only 3 rigid body motions, and corresponding to each rigid body mode there would be zero eigenvalue. So that is how I am saying 3 zero eigenvalues, and which are physically correct rigid body mode, corresponding to physically correct rigid body modes.
Okay, sir.
Yeah. So suppose no, if you have an element which has got 5 degrees of freedom, let us say u naught, v naught, w theta x and theta y, then it will have five. No, the of course the stiffness matrix size will also be larger, and then there would be five rigid body modes. Yeah. Yes. Someone was asking a question.
Sir, is it that free condition?
Yeah, it is free. So when I am talking about the eigenvalues of the stiffness matrix of the element, then element is free. There is no boundary conditions.
Okay.
Yeah.
Sir, one more thing, you told that if under integrated for thin structures, it will predict accurate results.
Yeah.
So, sir, like, how do we know like this thing? Like, do we have something to compare with?
Yeah, no,
Because
you
like
can
when we are
compare
doing
with
analysis,
you can compare with the exact analytical solutions or the results away. Yeah, one thing is to compare with the exact analytical solution. So for certain boundary conditions, the exact analytical solutions are available. So you can compare with those solutions. And when you are saying exact accurate is in comparison to corresponding analytical solutions, exact analytical solutions,
okay, sir.
using no, the theory of plates solutions.
Okay, sir.
Yeah. So now, as I said already, that for whether it is a 4-noded element or 8-noded element, the correct number of rigid body, modes is equal to 3. So that means if there are no problems with the element, then the number of the zero eigenvalues should be 3. Number of zero eigenvalues. These zero eigenvalues correspond to zero strain energy. So number of zero eigenvalues is equal to 3. And I have already told you that the 3 zero energy or rigid body modes correspond to translation along z, rotation about x-axis, rotation about y-axis. So 3 zero energy or rigid body modes. Rigid body modes are number 1, translation along z. The plate translates as a whole, translation along z, and second is rotation about, so plate rotates as a rigid body, so rotation about x, and third is the rotation about y axis, about x axis and y axis. So now this is the correct number of rigid body modes, but what happens for under integrated stiffness for thick plates? So what we see that, but for under integrated stiffness for thick plates, we get more than 30 eigenvalues, more than 30 eigenvalues. And these extra, whatever extra zero eigenvalues, and those modes, when you look at, they will not be physically correct rigid body modes. So extra zero eigenvalue modes are known as spurious or hourglass modes. Extra zero eigenvalue modes. Eigenvalues would be zero, and the modes, the corresponding modes, that is eigenvectors, when you look at, they will not be corresponding to, they, you cannot interpret them as rigid body modes, so they will have zigzag pattern, and that they are known as spurious modes or hourglass modes. So we get more than 3 zero eigenvalues, and these extra zero eigenvalue modes are known as spurious. So they are not correct. So that is why spurious are hourglass modes. This terminology you will also find in many of the plasticity problems and incompressible elasticity problems. Even no, the 3D elements are 8-noded 3D brick element is no under integrated. Just use one integration point. So in that also you will have these hourglass modes, and then you have to add an additional stiffness to overcome this hourglass problem. So I think at this stage, I would, although see the one assignment is already due, I would not like to point out to you. Although I will formally give this assignment in grade scope little later, but let me tell you that to study this, whatever we have discussed due to reduced integration, whatever problems. So there would be assignment 2, and in this you have to find zero eigenmodes, find zero eigenvalue modes, and then identify correct, physically correct rigid body modes and spurious modes or hourglass modes. Spurious or hourglass modes. This is the assignment, and what you have to do, I know you can do this assignment in actually groups. So maybe group of I think 4 students. So there are 9 different cases you can have. So one group can take just one case. So you have say a 4-noded element we have already talked about, 4-noded element, and then now in this you can do full integration. So one group can just take full integration case, and you just have to take a single element basically. And then the 4-noded element you can do this reduce integration, that is both bending as well as the transverse shear stiffness are evaluated using a lesser number of gas points. So, and third is you can have this 4-noded element where you use selective integration. Then now you can take some group can take 4-noded element, and then full integration, and then 5 is again 8-noded element, reduce integration, then 6 is again 8-noded element, selective integration. And then now some groups can take this 9-noded element. So similarly, you can formulate a 9-noded isoparametric element. You will have one node at the center. So that would become 9-noded element. And for this full integration, 9-noded element, reduce integration, and 9-noded element, selective integration. Selective integration. Yeah, so now you can think of now working in this. So the earlier assignment is on classical plate theory, and this assignment is on first order shear deformation plate theory. So this is what I wanted to. So there are also actually sometimes we prefer to use this reducer selective integration, but then we have to overcome the hourglass problem. So to eliminate this hourglass thing, there are methods to overcome that. And maybe that means we need to, because stiffness is under predicted, so we add an additional stiffness term or damping term to so stiffness term is basically for static and problems with low strain rate deformation. You use the stiffness matrix, additional stiffness matrix to overcome hourglass, and for high strain rate problems you use kind of additional damping matrix to overcome the hourglass problem if you are using the selective or reduced integration technique for thick plate problems. So that is how it is actually overcome. So this was one method. So there are two other methods. So the second method I had said to
Sir,
overcome the locking. Yeah,
sir, one thing.
yeah,
Sir, like how will we like find that which one are hourglass modes? Like, how to
yeah.
differentiate between the real, like the true modes,
Yeah, so
true.
so now if you see, as I said, you can identify from the modes that whether they are correct rigid body modes or not. So whether the mode is corresponding to a translation of the plate along z direction. So you would know you will find that the W values at all the nodes would be same. In that case, you will have the translation along z direction, and theta x and theta y values would be 0 in the eigenvector, so that would be translation along z direction. And then if you see the translation rotation about x axis, so you will find in that you will have theta y, which is the rotation about uh, the negative x axis, so that would be non-zero at all the, it would be same at all the nodes, and w values will be corresponding to, will be corresponding to that. So when you look at the modes, you plot the deformed shape of the element, so you will be able to identify whether no it is correct rigid body mode, or it is if it is not a correct rigid body mode, then it is an hourglass or spurious mode
Okay, sir.
with zero eigenvalue. Of course, non-zero eigenvalues will have some extraneous mode of the element.
Sir, here we are getting the rigid mode from KD equals to lambda D, and
Yeah,
uh, there we also get that from that free vibration KD equals to lambda MD. So both
yeah.
rigid modes.
So
So
yeah,
both.
actually, you can, from that also you will get the rigid body modes, correct, physically correct rigid body modes will be same in both cases, whether you solve KD is equal to lambda D or you solve KD equal to lambda M into D. Both will give you the same kind of correct rigid body modes, but the spurious modes can be different. So when we want to estimate, study the properties of the element, so we just find out the eigenvalues of the stiffness matrix, that is KD equal to lambda D.
Okay, sir.
Yeah. So now this is what I said, and this is most popular technique. So if you look at in the packages, you will find, for example, abacus. So in the element nomenclature at the end, you will have like R, and R stands for reduced integration. So and then if you, when you choose the solve a problem, you will also have the parameters to control hourglassing, so either stiffness parameter or the damping parameter to control the hourglassing. So when you hourglassing means we are applying some kind of nodal forces at the nodes of the element to reduce or eliminate the hourglass deformations, and so there would be some energy corresponding to that, and you will have to make sure that that non-physical energy which is coming because we are applying some additional forces to control the hourglassing, so that energy should be no less than, let's say, 10% of the total strain energy stored in the body. So that kind of a issue we have to check when you are using a software. So now the next method is, second method of eliminating the locking is known as consistent interpolation. Consistent interpolation. So that is the second method of eliminating locking. So now what we do in this is, so now we know already that the transverse shear strengths are gamma xz is del w by del x plus theta x, and gamma yz is del w by del y plus theta y. So because in the transverse shear strengths, the derivatives of w are involved, and theta x and theta y are coming without any derivatives. So we should have different interpolation for w and theta x, and the interpolation of theta x and theta y should be 1 degree lower than the interpolation of w. So let us say if w is quadratic, theta x and theta y should be bilinear. So that kind of an interpolation is known as consistent interpolation, and that eliminates locking. So let me explain that. So now in this inconsistent interpolation, what is done is, so let me write that in what I just said. Inconsistent interpolation, theta x and theta y are interpolated 1 degree lower than w. That is why, see, if the w is quadratic, theta x and theta y are linear, bilinear. 1 degree lower than w. So this eliminates locking. So now what I am telling you, let me explain you first for a rectangular element in physical coordinate space. So let us say we have a rectangular element in the physical coordinate space, and this is say x and y. These are the corner nodes, 1, 1, 2, 3, 4, and then there are mid side nodes, say 5, 6 and 7, 5, 6, 7 and 8. So what we do, because no, we want to use w as quadratic, so for that w will be interpolated using the degrees of freedom, w as a degree of freedom at all nodes. So you would see that the corner nodes will have w theta x1, theta y1, w2 theta x2, theta y2, these degrees of freedom. Similarly, corner node w3 theta x3, theta y3, and node 4 will have w4 theta x4, theta y4. But the mid side nodes will have only w degree of freedom. So here w5, w6, w7 and w8. So now corresponding to w there are 8 elemental degrees of freedom, but corresponding to theta x and theta y there are only 4 degrees of freedom in the element. So we will know when we write an approximate solution. So w is approximated using a quadratic polynomial. So 8 term a0 plus a1x plus a2y plus a3x square plus a4xy plus a5y square plus a6x square y plus a7 xy square. So this is theta w, and theta x will have only 4 terms in the approximate solution, because corresponding to theta x and theta y we have only 4 elemental degrees of freedom. So theta x would be interpolated as b0 plus b1x plus b2y plus b3xy, and similarly theta y would be c0 plus c1x plus c2y plus c3xy. And now when you why the locking is eliminated in this case, so let us investigate that. So now if we look at gamma xz, which is del w by del x plus theta x, and when you differentiate w, you will get with respect to x, you will get a1 plus 2a2x plus a4y plus 2a6 xy and plus a7y square. This is del w by del x, and of course theta x is b0 plus b1x plus b2y plus b3xy. So you will see here that no, the constant term has got contributions from both del w by del x and theta x. The linear term in x has got contribution from both. Linear term in y had got contribution from both. A bilinear term xy has got contribution from both. So now without no individually b0, b1, b2, b3 going to 0, the gamma xz can tend to 0 when we use this element for thick plate problems. So there will not be any locking in this case, because none of these b0, b1, b2, b3 are going to 0. So the element the will have element will have the bilinear variation of theta x throughout the element, and it will not go to 0, and therefore the locking will not be there. So the element will predict accurate results. So similarly, if you look at the gamma yz also, so that is, if you look at del w by del y plus theta y, so you will see this will be a1 plus 2a2 into x plus a4 into y plus 2a6 xy and plus a7 into y. I'm sorry, I'm writing a different thing. I'm sorry. So this will be a2 plus a4x plus 2a5y plus it is just the differentiation of a6x square and plus 2a7xy. You're just differentiating w with respect to y. So we will have 2a7xy, and of course theta y is already c0 plus c1x plus c2y plus c3xy. So we will again see the constant term has got contribution from both. So without individually a2 or c0 are going to 0, the constraint gamma x yz tending to 0 can be satisfied. Similarly, the linear term in x, linear term in y, bilinear term in x and y. So none of these c0, c1, c2, c3 will go to 0 when gamma xz is yz is approaching to 0. So the element will not depict any locking. And how you implement this? So for that, actually, no, again, rather than this, for explaining you why the locking is not there in case of consistent interpolation, I took this formulation in the physical coordinate space, but you can actually formulate the element in the natural coordinate space. You can have isoparametric element. So that means you map the element in the physical coordinate space to the natural coordinate space. So corner nodes are used to interpolate all the three variables, whereas mid side nodes are used only to interpolate w. So you have 1, 2, 3, 4, and 5, 6, 7, 8. These are the local node numbers, and this element is mapped to, as you know, in the square in the natural coordinate space. So you have xi and eta. So corner nodes and mid side nodes. 1, 2, 3, 4, 5, 6, 7, and 8. So now in this, what you will do, you will interpolate w as summation I going from 1 to 8 ni wi. So the ni would be say functions corresponding to 8 noded element. Whereas now when you look at theta x would be interpolated I going from 1 to 4, let us say mi into theta xi. Mi's are the shape function corresponding to 4 noded element, only corner nodes. So similarly, theta y would be I equal to 1 to 4 mi theta yi. So in this, I have already told you that the ni is the interpolation functions for 8 noded element. So we have already discussed these how to write these interpolation functions. Interpolation functions for 8 noded element, and mi are the interpolation functions corresponding to interpolation functions for 4 noded element, isoparametric 4 noded element in the natural coordinate space. So now know the shape functions you already know. So for example, if you look at the we have already written, so let me write just one. So like n1 and n1, n2, n3 and so on would be minus 1 upon 4 1 minus xi, 1 minus theta, and 1 plus xi plus theta. And like that, the other shape function. Similarly, m1 would be 1 by 4, 1 minus xi, 1 minus theta, and so on. The other shape functions would be like that. So now when you look at the development of the element level governing equations is exactly the same what we talked about earlier. So if you look at the kappa no, tensor can be written in terms of B matrix. So the form of the B matrix, if you look at, so this will be the B matrix. And if you look at the degrees of freedom, so now the degrees of freedom first for the corner node, so W1 theta x1 theta y1, and we will have, yeah, so W1 theta x1 theta y1, then W2 theta x2 theta y2, W3 theta x3 theta y3, W4 theta x4 theta y4. So these are first the corner node degrees of freedom, and then the mid side. Mid side nodes have only W degree of freedom. So W5, W6, W7, and W8. So this is what your vector of elemental degree of freedom would be. And when you write kappa is del theta x by del x, so that would be 0, del m1 by del x, 0, 0, del m2 by del x, 0, 0, because this is del theta x by del x. So del m3 by del x, and then 0, 0, del m4 by del x, and then 0, and then the 4, 0 corresponding to w. So this is the interpolation of del theta x by del x. Similarly, del theta by del y would be del m1 by del y, 0, 0, del m2 by del y, 0, 0, del m3 by del y, 0, 0, del m4 by del y, and then 4 zeros. And then the the kappa xy, that is del theta x by del y plus del theta y by del x, would be 0, del m1 by del y, del m1 by del x, 0, del m2 by del y, del m2 by del x, 0, and then del m3 by del y, del m3 by del x, 0, del m4 by del y, del m4 by del x, and then 4 zeros. So this is, you can say that the kappa vector tensor is B into DE. So I have shown you how, and other, the stiffness matrices are similar. So the stiffness matrix, load vector, everything you can write in a similar manner. So this is how you will write, your kappa matrix. And so similarly, you can write your gamma. The transverse shear strain terms would be equal to this BS matrix and into DE. The DE is same what we have defined over here, that this DE. So I know you can now write that. Let me just write few elements and then you can complete it. So because gamma is del W by del X plus theta X, so we'll have del NX, del N1 by del X and M1, and then 0, del N2 by del X, M2 and 0, del N3 by del X and M3 and 0, del N4 by del X, and then M4 and 0, and then 4 zeros. So like that, now you can write the other row also. So this you can say is going to be BS into DE. So yeah, now if you use this element gives you the accurate results for both thick as well as thin elements, and you use full integration. So for this element, use full integration for all the energy terms. For consistent for consistently interpolated element, full integration is used for all stiffness terms, that is bending as well as the transverse shear. and the advantage is it does not create any problem. So this element predicts accurate results for both thick as well as thin problems. Element with consistent interpolation predicts accurate results Of course, when I say accurate, you have to use the sufficient number of elements. That means you'll have to do the convergence study. Results for both thin and thick plates. Thin and thick plates. So there is no locking or hourglass kind of a problem what we have seen earlier. So I think this is where I want to stop. And now if you have any questions and doubts, you can ask. So the next class I will be talking about the third approach for eliminating locking, that is the modified interpolation approach, or that is also known as field consistency approach. So that is what I will be discussing in the next class. If you have any doubts and questions, you can ask.
So, sir, this is a totally different element than isoparametric element.
This is also you can see kind of we cannot call it a isoparametric because in the field variable itself for w we have different kind of an interpolation, and theta x and theta y we have different interpolation, and no the maybe the x and y can be interpolated using m1 m2 m3 m4, that is corner nodes, or xy can also be interpolated using the mid side nodes also. So no, it is similar to isoparametric element, but not exactly isoparametric element. We are still having when we are talking about this element, we still have no element in the physical coordinate space, element in the natural coordinate space, and the corresponding nodes, corner nodes, mid side nodes. Only difference is that no, the theta x and theta y are only interpolated through the degrees of freedom at corner nodes, whereas the w is interpolated using all the nodes, corner as well as mid side nodes.
Okay. Then, sir,
Yeah.
it can be used in curved surfaces.
It can be used in curved surfaces also. Yes, we can use this element for modeling the curved surfaces cells. I will be talking about that also, that how to model a curved surface or a cell using the assembly of flat plate elements. So before assembly you transform the stiffness matrix into a global coordinate system and then you assemble. So through that you can model the curved surfaces also. Yeah. Any question? Anybody?
Hello, sir. Why we are not considering that other degree of freedom on mid-side node?
Because we want to have a quadratic polynomial for w and bilinear polynomial for theta x and theta y. So essentially what we want to do is, in this case we want to take w as say like a0 plus a1 xi plus a2 eta plus a3 xi eta, no, let me say write that as xi square. So a3 xi square plus a4 xi eta plus a5 eta square plus a6 xi square eta and a7 xi eta square. So now for w we have the 8 constants, and these 8 constants are expressed in terms of values of w at all the 8 nodes. Whereas for the element, to make the element consistent, we want to interpolate theta x using only the bilinear polynomial. So we want to write that as b0 plus b1 xi plus b2 eta plus b3 xi eta, b3 xi eta. Why this is so? So that del w by del x and theta x, del w by del y and theta y, you have the consistency, which I already explained you. Now here, when I was talking about this and this. So we wanted to make sure that individually these constants b0, b1, etc. and c0, c1, etc. do not go to 0. And that when gamma xz and gamma yz are approaching to 0. So because in this interpolation, when W is quadratic and theta x and theta y are bilinear, so the transverse shear strain terms have contributions from both fields W as well as theta x or W and theta y. So individually the terms are not going to zero. So now since we want to have this kind of an interpolation, so now see in the theta x or similarly in theta y, C0 plus C1 xi plus C2 eta plus C3 xi eta, we have only four unknown constants. So these four unknown constants will be expressed in terms of values of theta x and theta y at the corner nodes. So that is why corner nodes have W as well as theta x and theta y degrees of freedom, whereas the mid side nodes have only W, because theta x and theta y we want to have only linear, so we are interpolating in terms of only corner nodes. Is that
Understood,
clear?
sir.
Yeah.
Yes, sir. Thank you.
Hello, sir.
Yeah.
Sir, as you've told the two methods, so which method is more suitable for thin and thick plates? How can we judge which method is more suitable? Is it related to some computationally
Yeah,
efficiency
see,
or?
actually, if you look at the reduced integration, it is straightforward. Because no only thing in the you have two different set of loops for integrate getting the bending stiffness and the transverse shear stiffness. So in the transverse shear stiffness evaluation, just change the loop variable and things are done. So the programming wise it is much easier, and the computationally also you would be integrating at, you will be evaluating at lesser number of gas points, so the element level calculations are actually lesser. So that way, the reduced integration or selective integration technique is preferred. But it has problems, as I told. That we have already discussed that what are the issues with thick problems. The thick plate problems if we are taking under integrated element. But in case of see this consistent interpolation element, you have to deal with in your if you are developing your own program, then you have to have different set of degrees of freedom at different nodes, and you have to take care of that in the assembly and everything. So that is more involved, the consistent interpolation element, whereas this reduced integration is straightforward. So the softwares, if you look at most of the softwares have only this reduced integration elements to eliminate the locking problems, and then of course they add additional stiffness or damping to reduce or eliminate the hourglass modes, hourglass deformations.
Okay, sir. Got it. Thank you.
So anybody, any other question? Okay, so if there are no questions, I am stopping here. Thank you all for your attention.